Okay, let's get started. Good morning, everyone. Thank you all for coming. Before I start, I have one minor announcement. Unfortunately, or fortunately, food and drinks are not allowed in this beautiful auditorium. So please take the food and drinks after we are done with the seminar. And we'll make sure that the signs are posted next time. Okay, thank you. With that, let's get started. I'm delighted to be here. And thank you all for coming to make this a wonderful event that it is. Just a few comments on what this is all about. This is a seminar series sponsored by and strongly supported by the Department of ECE. And thank you, Bill, for all the support. And the origins of this seminar series were, we would like to take the credit, but it came from Department of Physics. I'm not sure if any representatives from, thank you. Inga is not here, but Naresh and all these guys who have been doing this for many years got many of these ideas from her and her colleagues. Thank you all for that. With that, let me get away from the main event. We are delighted to have Alex. Alex Schwing is a relatively new addition to our family here in the Department of ECE. He graduated with his PhD from ETH in Zurich. And he did his postdoctoral studies at the University of Toronto. And he is the brains behind CSL, at least. And he's going to share with you a lot of things that he does from day to day, especially how to make intelligent systems. Okay, with no further ado, let's give a warm welcome to Alex.
All right, thanks so much for the introduction. How are we doing on sound? Can you guys hear me in the back? All right, perfect. So I guess first and foremost, I should obviously thank all the magicians that are behind the work that I'm going to talk about today. And those are all the graduate students in my group and graduate students from other groups here at university as well. Some of the people that I would like to mention are also in the computer vision group from the CS department, Derek Hoy, David Forsyth, and Lana Lasepnik. Also people in the EC department that I'm working with, like Naresh, who gave a talk last time, Professor Min Do. I don't see him here. But there's a whole lot of people that are behind this. So I don't want to take any credit away from those people. So really the magicians are all the folks that are the students that are here on the slide. All right, with that being said, I kind of want to start a little bit, in the past somewhere. About 10,000 years ago, our ancestors were still hunters, using tools like spears to survive in their daily challenges. And eventually, we started to settle down, growing corn and domesticating animals, and further refining the tools that we use on a daily basis. Right, and eventually those tools became so refined that we are transporting goods, very heavy goods, all across the world. And that didn't happen too long ago. And until just very recently, when we started to connect our tools together to quickly exchange information all across the world. And now, what did that translate into? Well, that translated into us gathering a lot of data. And I want to share a couple of statistics regarding the amount of data that we're gathering. And one of the facts that I was very surprised about to hear is that there has been more data created in the past 2 years that has been created in the entire history of the human race. And I think that is a pretty impressive fact if you think about that. Another fact that I think is pretty interesting is that every minute, 300 hours of YouTube videos are uploaded to YouTube, which I think is pretty impressive too. Who is watching all that stuff? Yeah. Well, I wouldn't know. And another interesting kind of forecast is in 5 years, we will have 50 billion smart connected devices. And obviously, they are recording all our life, all the time. Now, that poses an interesting question, right? What can we and what do we want to do with all this data? And in this talk, I want to go a little bit through what can we do and what do we want to do and what are the consequences of this. So in order to see what can we do with this, well, let's first start with, what is common to all those ages and what do we think is common to all those ages. Now, if you look through the tools, you can see that I'm always saying we were using passive tools. Tools like the spares, the plows, the steam engine, and the computers. Those are tools where you need to press a button. You need to use force in order to make something happen. Without you pressing a button, nothing is going to happen. And we're using those tools to develop new technology. But I would argue that this is very time-consuming. And therefore, one of the things that we should be going towards is what we call active tools. Tools that help us semi-automatically, in the broadest sense, develop new technology. Tools that help us support healthcare. Tools that improve our education. Right? And one aspect that I'm going to talk about a little later in this presentation is a mechanism that looks at images, like the one that I'm showing you here on the slide, and asks questions about this image. Right? And you can imagine using that in an education system in order to keep kids engaged, for example. Or to enhance manufacturing. Another thing which I'm going to talk about a little later is an application where you're given images with large pieces missing. And you're asking a computer to fill in the missing pieces without you sitting down and drawing every single pixel. In a sense, the computer knows for this application what a face looks like. And it can hallucinate whatever is missing. And I'm going to explain to you how you can design systems like this. And in general, active tools help us to address those tasks where many solutions are viable, right? In both those examples that I'm showing you here, there is not a single question that fits an image. There is not a single in painting that represents the missing parts. There's many options. So which one do we choose and why? All right, that was kind of a quick introduction. Now for the roadmap of this talk, I want to obviously tell you and talk to you about artificial intelligence. Where did it all start? Where are we now? And where do we want to go? And I want to make this talk very interactive. It's pretty boring if I'm just standing here and talking. So maybe let's discuss a little bit about when did you guys think AI started? What was some of the events that you recall where you would say, hey, this was for me artificial intelligence? Turing test, that's an event, and I'm going to mention that a little earlier. That was, Alan Turing coming up with a test to demonstrate what an artificial or an intelligent machine should look like. In fact, we're going to do something like a Turing test a little later in this talk. What else do you know?
Maybe preloading questions on Google when you start typing?
Preloading questions like Google, that's right. How does Google do that, right? How do they, you start typing something, and then they come up with suggestions. How do they know those suggestions? Those are examples very related to what I was showing earlier, right? Asking many questions about an image. Very similar there. Very good, very good. Other things that you use on a daily basis.
Well, computerized chess, or playing against those.
Right, exactly. And this is a very, very exciting area, right? It started, and I also show a couple of events regarding to game AI. It started actually very early on in even before the 1950s. Then I guess the computerized chess, one of the main events there was Deep Blue in 1997, I think. And just more recently, Google DeepMind with their AlphaGo and AlphaZero series, where they have a mechanism that learns how to play Go and chess, and shogi was, I think, the third game. Other events, yes? Right, exactly. If you go to websites like Amazon, right, they show you products that you might be interested in buying based on what you have bought and based on what other people bought that was similar to what you have been looking at in the past. Other things that you recall? No?
I did a phone call that I couldn't tell if it was a computer or a human.
Right, there's all those chat systems these days, right, where you receive a call and you don't know is that a computer talking to you at first, or is that a person talking? That's right. Alexa, right? That's another important one. We are talking to our devices these days, and sometimes they have trouble understanding what we want. At least they have trouble understanding me. But yeah, there's plenty of those devices that we talk to.
So, in politics, where do you want to put your money, advertisement or kind of campaign, kind of identify the demographic kind of data?
Right, exactly. In politics, I guess that is an area that I should be careful about what I'm saying here, which kind of got under fire a little bit lately. That's right. So there's many events where we're using those systems these days. And one of the questions is obviously, why is data necessary in all those areas? And I think part of this talk, I want to bring this across a little bit. Why do they need all the data that they are gathering, and why should we be careful about that? All right, so let's look a little bit in the past, right? Naresh, in his talk 2 weeks ago, talked about the golden 40s. I kind of call it the 30s to 50s. And what happened in that area that is even present nowadays? So one of the things that neurology research showed was that the brain is essentially an electrical network of neurons. Right? That was one of the events that happened back then. Now that got people thinking. Why did it get people thinking? Well, there was another area, it's called cybernetics, and in particular Norbert Wiener, who described the control mechanisms and the stability of electrical networks. Now, together with information theory put forward by Claude Shannon, who described digital signals, and the theory of computation coming up from Alan Turing, who described the digital nature of computation, you can see that putting all those things together, people obviously started to think, well, can we build brains artificially, right? Since neurology showed us that the brain is just an electrical network of neurons, and we know that electrical networks are stable, we have an understanding, at least a preliminary understanding, of how to transmit signals and what computation means. It seems straightforward that we should be able to build an electronic brain and a neural net. And that was put forward by Walter Pitts and Warren McCulloch. Now in that area, game AI was already popular. Now I want to highlight to you that there was no computer back then. Still, people started to build systems that were able to play checkers or even chess already back then, without computers in the way we know them existing. But those were very specialized areas. And then many people date the beginning of AI or the beginning of machine learning to actually this event, which was a proposal written in 1955 and then eventually funded, and the event happening in 1956. And that's actually fairly interesting to read. It was put forward by John McCarthy and Marvin Minsky, both of which were very forward-looking, and I'll show you in a bit why. But what they wrote was they proposed a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956. And it goes on and on, talking a little bit about an attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now restricted to humans. And they estimated that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. Now that was a little bit ambitious, I would say. That did not quite work out. I guess lucky for me in this case. Otherwise, I probably wouldn't be here. However, this document contained a lot of important aspects which we're still doing research on today, and some of which I want to mention. Automatic computers, right? I told you that computers didn't exist back then. Still, they were thinking about it in the way that is very much, or in a way that we could even think about it today. Programming languages was part of this document, and it did not exist back then. Neural nets If you're following the news lately, then you can see or read about deep nets very frequently. Neural nets are something like deep nets. Theory on complexity of calculation was another thing that they mentioned. Self-improvement, in fact, those are mechanisms that are built into some of those chess engines and Go engines. So there's research on this today. Abstractions, you could argue that neural nets compute abstractions of layers, and randomness and creativity. Aspects which we don't have a good handle on even today. Yet I will show you some of the work which also people here at UIUC are doing in this area. One of the people that I want to mention here is Arthur Samuel, and you get to see why I want to mention him. And he came up with a pretty good checkers player program in 1959, and that used mechanisms like search trees, alpha-beta pruning, and self-play, mechanisms which we still use today in many of those systems. Now, he implemented all this on 9 kilobytes of memory, which I think is pretty impressive. And if I give my students a computer with 9 kilobytes of memory, they'll probably throw it away. The reason I want to mention him is because he was at UIUC from 1946 to 1949. I was definitely not around at that time, but maybe some of you were, and maybe you even know him. Now, present-day incarnations of what he was doing are depth-first search, iterative deepening, breadth-first search. Those are just a bunch of algorithms. And if you read some of the more scientific publications in that area, you see some of those terms, which are not important for this presentation. I just want to bring them up in case you're familiar with that area. Then you can think about him having invented many of those. Now, this conference that I was talking about, the 1955 conference, kind of sparked quite some interest in that area. And so the subsequent area was called the Golden Years from 1956 to 1947. A lot of inventions were made in that area. However, eventually everything had to come down. And I guess part of it was a book written by Marvin Minsky, and one of his comments in the book saying in from 3 to 8 years, we'll have a machine with general intelligence of an average human being. Well, again, people were very forward-looking. They were very excited. But they were, I guess, a little too ambitious considering the amount of data that people had and their compute capabilities. And that caused the first, or what is called the first AI winter from 74 to 1980. Now, what were some of the problems that you could think about at that time? Storage, that's right. Storage is one big problem, right? I mentioned 9 kilobytes. What can you do with 9 kilobytes of data? Other problems that you can imagine. Speed of computers, that's right. Those problems that they're trying to tackle have what is called a combinatorial explosion of possibilities, right? How to address those with computers that you had to manually solder together. It's just not feasible. A lack of, I would put it as a lack of an understanding of the algorithms, a theoretic understanding of the algorithms. That's right. Those are all missing parts.
There was a bad economy at the time with stagflation.
That you tell me.
You were in the U.S. then, right?
I don't recall. Let me put it that way.
Well, we were really into the space program. How are we going to do all this? Sputnik had gone over, and now we were really moving.
Right. So I guess some of that is also related to other areas becoming hot and some areas being less exciting. Those are certainly true. So what I put down here as the problems are, and all of which you mentioned, is limited compute and memory, right? They were trying to build natural language demos, which had 20 words, because they couldn't fit more into the memory back then. How do you do something with natural language if you have to deal with 20 words, right? That's just, by now we would probably say that's not enough. Combinatorial explosion, I mentioned that, and it was put forward by you guys. Encoding of common sense knowledge, right? Databases didn't exist back then. neural nets couldn't solve very simple tasks, right? Disambiguating very simple objects wasn't feasible back then. Obviously, after winter, there's a boom. Boom from 1980 to 87 was mainly put forward by some inventions of John Hopfield, Jeff Hinton, who showed how to train those neural nets more effectively. And then expert systems were restricted to a small domain, for example, deep thought for chess. In the earlier ages, people were trying to build systems that could address all the problems, oftentimes. And this changed back then when they looked at specific tasks and were trying to solve those specific tasks. So deep thought is kind of the predecessor to Deep Blue, who later on went ahead to beat even the best of us. Now, eventually, things didn't work out that well anymore in 1987 to 1993, and that was mainly due to computers coming up. Everything I talked to you about before was systems that were manually built for a particular task. So you can imagine that this is just not scalable if you have to build a system for every separate task. So computers came around. It took people a while to understand how computers worked and how to use them for this particular problem. And so there was just a shift of interest and a shift of focus. That is, yes, that's probably true as well. Where it was more about gaming and graphics that were the exciting areas. Yes, that's a good point. That I should know. Okay, and then kind of now going somewhat more quickly through this, 1993 to 2001. Some of the important events that you may recall, and I mentioned that before, is IBM's Deep Blue. Some more technical things like data sets that people started to collect. MNIST is a data set for digits. 2001 to present, some of the events that you also may recall is IBM's 2011 event, Jeopardy, DeepMinds. I put it 2016. The Atari games were slightly earlier. AlphaGo and AlphaZero we talked about before. Now, one of the things I want to share is particularly these DeepMind series of computers playing games, right? And that was an event a paper that was put forward in 2013, where the folks at DeepMind, they took one algorithm and they trained it on a series of 40-something games, Atari games, and they wanted to figure out, can a single algorithm learn how to play all those games? And so one of the things which I think is pretty impressive is looking at what this algorithm learned for playing Breakout, right? You guys all probably know Breakout. At the beginning, the algorithm is very stupid, right? Doesn't really know much and doesn't really understand the game. Now, you train this system a little more, and by training, I mean you have this system just playing a couple of times, and it eventually starts to understand more of the game and what it's supposed to do. And it has a reasonable idea of what's going on. It's still somewhat shaky, but that's OK, given that it has played, I guess, 200 times. Now it has played 600 times, and then interesting things happen. Just like, at least myself, being somewhat lazy, this guy also learns how to be lazy. He kind of digs a hole, and then he puts the ball up the hole, and is just waiting. And he keeps on, doing that, and then pushes the ball back up the hole and just waits for what's going to happen. Now, how do people do all those things, right? What is kind of the main underlying mechanism behind that? And I want to go in very simple points through that. And the example that we're going to use is, given an image, how can we recognize a cat in the image? All right, so let's try to do that together. Here's an image. How do we recognize cats? Eyes. OK. Well, I guess the first question we actually need to answer is, we know it. We look at that picture, and for us, it's fairly intuitive what this picture looks like. But how does a computer actually see that picture? Digits, that's right. It's like, a chunk of numbers, right? And before we go there, I'll show you a demo of this. Let me call this image, in mathematical terms, x. And what we want is really putting this image into a function, and out comes an answer. right? What answer do we want to have as output? Well, in this case, we want to have cat. Let me call it yes. It's a cat, right? We want to answer that question. And we want to have an answer from what we often call an output space, right? And the output space, we call it y, or calligraphic y. In this case, it's 0, 1, or no and yes. OK, here's another image. What do we want to have as the answer? Yes, that's right. Here's another image. All right, no, right? OK, good. So question is, how does this function look like? Right? This function takes an image as input, and it's supposed to produce 0, 1 as output. How does this function look like? Any ideas? Isn't that why I'm here, was the comment? Yes, I guess that's partly why I'm here, to tell you what this looks like. OK, so to answer that question, let's first look at how does an image look like for a computer. It's a chunk of numbers. In fact, every single one of you can simulate what an image looks like for a computer, and I want to show you guys real quick. Let me see whether that works. Now, many of you are probably familiar with things like this, right? That's a spreadsheet. You can go onto Google, or if you have Microsoft Excel or any one of those other programs, right, you can use a spreadsheet, right? You can put numbers in there. I can put the number here. There's a digit. Now I can put many numbers into this spreadsheet, and I can use what is called conditional formatting, right? If that number is low, I'm going to make that cell very dark, and if that number is high, I'm going to make that cell very light. OK. I can also do color, yes, and I spent last weekend on doing that. I guess I shouldn't say that. They might not like me spending that much time on this. So I spent a lot of time doing this. So there's a bunch of numbers, right? Red, green, and blue. And I colored them depending on what the number looks like. OK. Now, I spent some time on this. I spent even more time on this. And I spent really a lot of time on this. And you can see that just by using these spreadsheets, right, you can come up with images. Right? And this is really how a computer sees an image. It just sees numbers, possibly in red, green, and blue. And you can create an image that way. All right, now let me see whether I can get back to this. All right, there we go. Right, this is what we saw. An image like this one looks like a spreadsheet. Right? We have dark cells up here that corresponds to numbers that are somewhat low. We have brighter cells down here that corresponds to numbers that are higher. And the numbers are generally between 1 and 256, or 0 and 255. All right, and in fact, that's really what an image looks like. If you take your phone, a microscope, and you look at the screen of your phone, that's what you're going to see. Exactly what I showed you in the spreadsheet. So your screen on the phone is a large spreadsheet, if you want. All right. Now we know how a computer sees an image. Let's see. Does it make it any easier to describe a cat? We need to figure out some form of patterns, right? Well, it's very hard to come up with some patterns, right? If I were to ask you, well, give me a pattern for a cat, what would you do? OK, we could try to come up with something and try, the nose seems fairly characteristic. But, the cat can rotate and do really weird things, and then we might not see a nose. So it's very hard to come up with some form of pattern. So as someone mentioned already, let's look at some data, and let's see what's happening, right? So still very hard to describe a cat. Let's look at more data. OK, here's my data set. And in my data set, I have X, which are our images. And I have the corresponding label, right? I asked someone to sit down and tell me whether a cat was in there. So I have a large data set. OK, here's our data set for the purpose of this presentation. That's our data set. That's everything I was able to collect and annotate. Now, the question is no longer, let's recognize cats. but the question is, let's recognize cats in this data set. Okay, now let's look at this data set. Is it any easier to recognize cats in this data set? That's right. Someone paid careful attention. I kind of came up with a contrived data set, right? There is these white squares here and those black squares there. So it's kind of very easy, yes? That's very good, and we'll get to that in a bit. You're kind of getting ahead of ourselves. That's fine. That's perfectly fine. So what I said was, let's recognize cats in this particular data set. OK, so let's answer that question. And as you guys are all smart, you already figured out, I kind of came up with a very contrived example. Now, you wouldn't do that in reality. I just did that for the purpose of this presentation.
So when a human being says, that could be a cat, I can't quite tell, maybe it's a groundhog or a cat, is that because the distance or not getting enough data points?
Wait a little bit with your question. I'll answer that in 2 or 3 slides from now. But very good question. So for now, we have this data set, and I kind of have this contrived example. So our function then is, right, if the bottom left corner is black, return no, otherwise return yes. But that would not correlate to cat. That's right. It just works on this particular data set. You guys are faster than I thought you are. All right, so let me quickly go through this. Right, here's one image in our data set. We look at it, yes. Here's another image, no. So it works perfect on our data set. Great. How about this image? What would be the answer? The answer would be, if the bottom left corner is black, return no, otherwise return yes. So that thing is probably not black, so we would return yes. Damn it, doesn't work, right? So this does not generalize. And I guess this is what many people of you are already saying. Well, I recognize, or I came up with this weird function, but this function does not generalize to cats. So I don't actually recognize cats. OK, so that's the problem. But what exactly is the underlying problem?
You have no idea what a human being is doing, and until you understand human performance on this task, it's not even defined.
OK, well, we'll take that question offline. I know.
So it's a problem that's too similar to cats.
I think, OK, one of the problems is that the feature that I used, bottom left color being 0, isn't really a good feature. It doesn't really tell us anything about cats or particular patterns of cats. Just use that feature to demonstrate what a simple classifier looks like. So if that feature is not good, what can we do? Well, we come up with more complicated features, more complicated patterns. OK, we just use more. Or more relevant ones, yes. For the sake of this task, I don't want to come up with more relevant ones, then it kind of becomes more complicated to imagine. But let's just say, OK, we have the bottom left color, we have the top left color, and many more. Let's just keep it 2-dimensional such that I can picture it. Otherwise, I have a problem of picturing these things. OK, so we have many features. Features that someone came up with, like the pattern of the nose, and so on and so forth. OK, and then I can put my cats and non-cats into this picture. OK, now how do I differentiate cats from not cats in this 2-dimensional picture? Exactly, I just draw a line between them, right? There's our line. In high dimensions, this works as well, right? I just have even more features, and I draw not a line, but in general, a hyperplane between them. OK, so now we kind of know how to classify cats. We just have this, in a sense, the same problem than before. We need to come up with the right features. Okay. We'll use a decade of PhD students to come up with features. Okay, one of the problems, I'll mention that in a bit. So what does it mean then? And oftentimes when you read some of the literature, right, you'll hear about training and learning or inference and prediction. What do people mean by those two terms? Right? And by training and learning, you're given this data set. Right? Here's our data set. And what do we want from this data set? We want to have this separator, right? So training means find this separator. That's the training phase. Now, what happens during inference and prediction? What are we given? We are given a new data point that we have never ever seen before. What else are we given? Right? We're trying to figure out which side of the line it is, but for that we also need to be given the line. So during inference and prediction, we are given the separator and a new data point. Right? This is what I'm seeing during inference, the separator and a new data point, and I have no idea yet, is it to the right or to the left? And then I'm trying to figure out what is the corresponding label. In this case, because it's below that line, it's going to be an X. Now, this task over here is typically very easy to do. If you're given the function, you just have to evaluate this is below or above that function. That task over here, finding the separator, is not that easy to do. It requires a lot of computations. All right, but one of the things which we realized is that the features are the most important ingredient. Right? Who comes up with those features? PhD students. All right, in particular, every task required its own specific features. If you want to detect a cat, you need to design your features. If you want to detect street signs, you need to design your features. So every single task requires hand engineering of features. What does that mean? Well, from a business perspective, that's not very scalable. All right, so that's why the whole progress was somewhat slow. The whole game changed in 2012. In 2012, Alex Gruszewski and company showed significant improvements on an important data set, which was called the ImageNet dataset, by using deep nets. The main difference to what people did before was they did no longer engineer features. They took the features, fed them into a neural net, which we have heard before, and they got the output. So there was no engineering of features anymore. And here is, I guess, this ImageNet classification task that I talked about. You're given an image, and you're asked to classify it into 1,000 categories. Right? There could be a cat in the image, there could be a dog, there could be a bus, a truck, a fire truck, 1,000 different categories. And the task is to figure out which one of them. So it's not cat versus no cat, but which of those 1,000 categories. Now, what people did before 2012 was engineering those features. And this is what is called shallow here, and you can see the performance that they got on this particular task. It improved gradually, more and more features coming around. However, in 2012, just by using deep nets, no engineering of features anymore. In fact, automatically searching for those features, they improved the performance significantly. And people got very excited about this. The year afterwards, they used a more fine-tuned deep net, improved the performance even further. Then eventually, they used deeper deep nets, 19 layers, improved the performance, 22 layers, 152 layers, gave them 3.57. Human performance on this data set, by the way, is like 5%.
What layers mean again?
I'll show you that in a bit. Here we go. So you're taking an image as input, and this is what that deep net, AlexNet, by the way, looked like. You feed in your image, and then you apply a sequence or a series of convolutions, a sequence of computations. So here, you take your image, you convolve it with a filter that is learned, you convolve it with another filter that is learned, and you keep doing some of those convolutions until eventually you end up with 1,000 numbers. And those 1,000 numbers are the probabilities for which category does it correspond to? And the depth of the deep net is the number of layers which you have. In this case, 1, 2, 3, 4, 5, 6, 7, 8.
So you said what percentage for humans versus what percentage for...
So if you ask, and the question was, what percentage did the computers achieve, and what, if I were to be a human, how good would I be able to do in this data set? So people tried this, and humans can do roughly at 5%. The main reason humans can do at 5% is, there's, for example, snakes in that data set, and they ask you whether this is, I don't know snakes, but rattlesnake and, tons of other types of snakes, and I have no idea how to disambiguate them, whereas the computer looking at those 1.2 million images gets very good at it. Same thing for dog breeds, right? It gets very good at differentiating not cat versus not cat, but even dog breeds. And as a human, I have a hard time doing that. Or I would need to be an expert on dog breeds in order to figure that out.
Why don't they just use like 1 million layers?
Good question. Why don't we just use a million layers? One of the reasons, so I'll answer that in a bit. The nice thing about it was we can automatically find those features, those representations. This thing has 200 megabytes of trainable parameters, millions of trainable parameters, and this is just 8 layers. Now, if you scale it to millions of layers, which would be exciting to do, you would need a lot of computational power and in order to process all that, and you would probably need a lot of data. And we'll show that. I'm boring someone. And so we need a lot of trainable parameters, and that means we also need a lot of data. I'll show a plot about that in a bit. What is the relationship between the amount of data and the accuracy that you can roughly expect?
In this data set, is it already labeled what the answer is?
Yes, this data set was already labeled. So you have 1.2 million images, and for every image, you know what type of object was shown in that particular image. That was the training set, yes. And part of this, and another part of the data was withheld, and there were no labels on this data set, and that was the test set. So one of the important things is obviously you don't want to train on the test set, right? The test set is kept separate. Now, another interesting aspect of this was people showed that this architecture generalizes, in quotation mark, to other tasks. So they used the very same architecture, applied it to other tasks, and they were able to show good performance there too. Obviously not the best performance, but you can what is called fine-tune it. But that was another important aspect. So different from before, we're no longer engineering features. We're now designing architectures. AlexNet, right? I mentioned 8 layers. VGG was the one that had 19 layers. GoogleNet, 22 layers. ResNet, 152 layers. You could scale it further, but at the expense of having a lot of compute to do, right? And that brings us to the computational needs related to the question that was asked. Inference is still very quick. I'm given an image, and I have to just pass it through this deep net. However, learning oftentimes takes days and weeks using expensive accelerators. And if you follow the news, then you might have read about NVIDIA's what is called DGX2. This thing has roughly 2 petaflops. Someone is excited. And this is just one machine. Now, how expensive do you guys think this machine is? Who wants to venture a guess? $200K, $300K, some billions. It's about $400,000. I would love to have that machine. I guess we don't have it. But that means, right, to train all those parameters, we need to process a lot of data, and processing that data takes a lot of time. And for that, all those machines are built these days. And if those crypto miners would spend so much time mining Bitcoins, we would get them at a reasonable price. All right, one other plot that I wanted to show related to a question is, why did it take so long for deep nets to take off? Right? And what we often observe is, the amount of data that is required to achieve a certain amount of performance. Now, if you have very little data, like over here, then you're actually doing very well with those shallow deep nets by just assigning or finding a few features and learning a few parameters. Shallow deep nets, they have roughly 50 to 100 parameters, and you would be doing very well. Now, the more data you get, the deeper nets you can train, and they obviously give you more and more performance. So one of the necessary conditions for deep nets to work is huge amounts of data. But as I started this presentation off, only very recently were we able to really gather large amounts of data. In fact, some of those big data sets, ImageNet, came around in 2009. So huge amounts of data are a necessity to make those things work. And with huge amounts of data, there's obviously a lot of compute that is necessary. Now, many applications then use those deep nets, and we can go through some of them, right? Spam or credit card fraud classification. Deep nets are used all the time. Another interesting article came up recently was dermatologist-level skin cancer classification. You take your cell phone, you take a picture of some part of your skin, you send it at a deep net, and it can pretty accurately figure out is this cancer or not cancer. At least at the same level as a dermatologist can. That's what people showed. Neural language processing, right? We're talking with, and very initially that came up with Alexa, or we talk to our phone. Deep nets are driving all that technology. Driving assistance, if you want to detect lanes in your car, deep nets are running there. Personal assistants, I already mentioned that. Game engines run those. Also, people that analyze your behavior. And this is where it starts to become scary. Well, we'll talk about that in a little bit. Just quickly going through some of the things that we are doing in our group is things like you're given a video and you want to figure out where are objects moving, objects that you're interested in. You have never ever seen fish before. So this algorithm doesn't know what a fish is. The only thing we are giving this algorithm is the first image, and we're telling him keep or track those objects. And then if I run this video, you can see the algorithm is actually able to track these objects despite significant deformations. And it has never seen fish before. It doesn't know what a fish is. Other interesting tasks related to virtual assistants. You're given an image and you want to figure out, where is a woman and you're asking for, or you're given a sentence like a woman in a green shirt is getting ready to throw her bowling ball down the lane. We want to figure out where are all the nouns in the image. Again, you use deep nets and you can pretty accurately figure out, here is the woman, here's the green shirt, here's the bowling ball, and here's the lane. And all this works very, very efficiently. Another task, image captioning. You're given an image and you want to describe the image. Now, one thing I should mention here is the algorithms generate those sentences word by word. So they're not picking a sentence from a large database of sentences. They're really generating these sentences word by word. If you read through those sentences, syntactically, they're perfectly fine. We did not tell this deep net what a correct sentence looks like. The deep net figured it out itself.
What is LSTM?
LSTM is long short-term memory nets. CNN is convolutional neural nets, and GT is ground truth. So that paper was about showing that convolutional neural nets work just as well as long short-term memory nets, having the advantage that convolutional neural nets are easier to train than long short-term neural nets. And GT was the ground truth that people used to describe that image. Now, one of the key things I also want to bring across in case you're interested in coming up with a business around this, data is the necessity. Any of the big four, whatever you want to call them, has huge amounts of data. Now, how are they running their business? Well, they use that data to train a model. Then they use that model and put it to use, getting new users. And from new users, they get new data. And from new data, they can train bigger models, and then this whole thing just runs. Now, the important aspect here is that you're in business as long as you have more data than your competitor, which is why many of those companies are set up such that they gather data from you. Okay, I guess I skipped through that. I want to briefly mention, the future towards tasks with ambiguous results, which is how I started off with. And this is a plot where researchers were asked, what do you think, what tasks are going to be feasible in X years from 2016? So I'm showing you on the x-axis number of years from 2016. 0 means 2016. And we can go through that, right? Angry Birds, some form of computer game. People thought in a median about 5 years, so 2021 or something like that. World Series of Poker. If you followed the news, you probably already know that we now have computers that play poker better than any human can. Researchers predicted in 2016 that this is going to be done in, 3-4 years. So that is taken care of. Folding laundry, playing StarCraft, people are looking at that, transcribing speech, even translating versus an amateur human. If you go online, you can buy those earbuds where you synchronize them with your phone and they translate automatically. Now, it doesn't work too well yet, but people are working on this, and what was it here? In 10 years from now, I'm pretty certain that this is going to be taken care of. Playing all Atari games, writing high school essays, generating a top 40 pop song. I'll show you some of the pop songs that machines can generate in a bit. Truck drivers, so if you think about becoming a truck driver, might not be such a good idea. Retail salesperson. Those are kind of the numbers that we're looking at. Looking a little bit further out, playing Go, same training as human. Playing Go we have taken care of. Same training as human we haven't taken care of, I guess. I mean, I'm not a Go player, so I don't exactly know what it means to have the same training, but those machines require a lot of computational resources. And I guess relating to Naresh's talk 2 weeks ago, he is trying to come up with computational mechanisms that reduce those resources. Retail salesperson, surgeon, math researcher. I guess I recommend becoming an AI researcher. Anyway, kind of showing off a few more results here. Right, I already showed you that task very early on. Given an image, you want to fill in whatever is missing, and we have algorithms that can do that pretty accurately. Or you're given a grayscale image. That's the ground truth colorized version of it, and you want to come up with algorithms that can color this. If you have images from the 1920s, you want to get a color version out of it, send it to us, we can give you a color version. And the algorithm, this is a comparison to other algorithms. Our approach does fairly well there. I already showed that one. Given an image, you want to generate questions for the image. You could imagine that being useful in the educational setting. Right, given an image like this one, the algorithm is able to ask, is the man wearing a helmet? What is the man wearing on his hat? What does the man have on his back? What kind of bike is the man riding? Again, those questions were generated word by word. We didn't tell the algorithm what a question looks like. It picked up automatically what is the syntactically correct form to ask a question. Creating a set of captions for a given image, right? We talked about that already. Creating dialogue. Right? One of the recent things that we looked at, we published that and actually later this year, is given an image and a few question and answers, can you design a system that can continue asking either questions or answers or both? And here we have the algorithm kind of talking to itself. Right, it starts off with what color is his hair? Brown. What color is the skateboard? Black. Is the dog a large breed or a small breed? Large breed, some type of lag max. And again, the algorithm figured out automatically that there is a dog in there, and I should talk about a dog. The algorithm figured out automatically there is a skateboard in there, and you should talk about the skateboard. We did not tell the algorithm that there is a skateboard or a dog in there. All right, we talked about composing music. Right, and I can show you a couple of things that algorithms come up with. We did not do that. That was done by a company called IVA Technologies. There is still some human effort involved in that, but if you look at that, it sounds, or if you listen to it, it sounds fairly realistic. I don't know whether sound works. Oh, there we go. it can kind of come up with what does a reasonable start of a music look like or sound like. And the only way it learned this is by looking at tons of sound snippets and what those sound snippets sound like. And you can go to YouTube. You can find this on YouTube. It takes about an hour. I don't think everyone wants to sit here for an hour, but you can listen to that yourself. Not only creating music, right? Creating art. People are looking into that too. Here's the Mona Lisa painted by, I guess you can guess, either Picasso to the left, Van Gogh in the middle, or Monet to the right. And you probably recall some of those images, right? This one by Van Gogh, and you can kind of see, well, it looks kind of similar. Again, and that was done by Justin Johnson and company. Now, I guess I promised we're going to do a little Turing test. That's one of the things that we did fairly recently. What I'm showing you here is X-rays. Which one is real? Which one is artificially generated? So what I'm showing you here is X-rays. I guess I'm showing you 10 X-rays. Yeah. And I'm asking, which ones did our algorithm generate completely from scratch? And which ones are X-rays that are acquired from a machine? The left ones are fake.
Are they pairs?
No, there is no pairs. In fact, all those X-rays that I'm showing you here are artificially generated. And one interesting thing that I want to point out is that doctors tend to put, little L's up here in the corners in order to identify where is the patient's left. All our algorithm did was running through hundred thousands of X-rays. We did not tell the algorithm to put L's there. It figured out automatically that doctors put L's there. I have to put L's there in order to make this thing look realistic. OK, here's a pair. Now, in this case, there's one realistic and one is artificial. We can play the same game. Which one is real and which one is artificial? Now I'm showing you really both. So I hear people saying the left is real. It's actually not true. The right one is real. The only reason I can recognize it is because we have an L here, we have an L here. In fact, that L is the wrong way, but there's even more details below the L, and our algorithm is not able to capture those tiny little details. So that's how I can tell. But if I look at the body, I'm not a doctor. I wouldn't be able to tell what is real or what is fake. So we did ask real physicians that have training in that area. We asked them, we showed them pairs, and we asked them what is real and what is fake. And over here, you can see the results. Here is the 25% line. You can see that many of them over here are around 25%. They classify the wrong one as real. There is some doctors, I'm not sure I would want to go to those, which clearly favor images that were artificially generated. And all that by just looking at large data sets and figuring out what is going on in this data. Now, we don't have to stop at X-rays, right? We can go further. We can try to hallucinate the entire world. OK, we're not going that far yet. So what we have here is also something fairly recent. Oh, I should kind of, does this play? Oh, yeah, there we go. We can look at apartments. What do apartments look like? And again, here we are generating chairs. We know that a table is in the middle of chairs. We did not tell the algorithm what apartments look like. And it figures out what those apartments look like. Sometimes it places, I guess, plants in the middle of a way. But I think it does a fairly reasonable job at figuring out, oh, there's a table missing, by the way, what apartments look like. Now, these are very preliminary results, but give us 1 or 2 more years, and we'll have that figured out as well. Now, the vision is obviously, to build self-aware algorithms that help us merge these hallucinations with the reality, right? If you close your eyes, you can put yourself into an environment, and then you can merge where you really are. In general, tools that help us search for solutions, tools that help us understand better what's going on. For that, we need huge amounts of data and compute. Now, one of the important aspects I want to highlight is that all this does only work with huge amounts of data. And these days, all of you are using data to pay for services. Right? You go to websites like Facebook, you upload your images, you give them your data in order to use that service. In fact, I would go one step further and even argue that we are forced to pay for services with data. For obvious reasons, while you may argue that at this point in time, that's okay, I can upload my picture. Think 5 years down the road. You're offered a health insurance where you have to pay, you get the health insurance for free, but you have to wear a wristband all the time. Would you go for that? Well, it's free, right? Now, the problem is, if you're wearing a wristband, they can gather personal data, huge amounts of personal data. And there's a lot of gold inside this data, I would say, right? Imagine you meet someone, your heartbeat goes up. They know who is in the area and what's going on. Whatever they want to infer from that. All right. Now, coming back to the very beginning of my talk, we eventually started to settle down. We figured out a model for what it means to own land, to buy land, to put the fence around it, to say you can come in, you can't come in. We developed machines, and we figured out a model for what it means to own machines. But I would argue that at this point in time, we have no model for what it means to own data. You cannot control what is happening to your data and where is it used. And I think this is one of the big problems that we all need to get started, and we all need to think about. How do we handle this? In particular, if it becomes to data as personal as medical data. And we need to be very careful there. All right, with that being said, I want to obviously thank you guys for being here. Thank the sponsors that supported all this research. Note there is a little bit of space missing here in case you know someone. Feel free to reach out. Thank you. I'm obviously happy to answer any questions. Can you repeat the question?
Sure. With the huge amount of data being created every second, how do you integrate relevant data into your AI model so that you use real time?
So the question was, with huge amounts of data being created every second, how do we decide, what is meaningful, what can we use and what can't we use? And in fact, that's one of the key aspects of machine learning researchers these days, trying to figure out what are the important pieces of the data, what can we use and what can't we use. Right? Curating that data and getting that data in the right format is hugely important.
Is there any safeguards about properly labeling training sets of data so that it's accurate in the real world and not just someone's political opinion or something else?
So the question was, is there any safeguards in terms of labeling the data and then, for example, not labeling it in terms of political views? Again, a very important question, and a question where we don't have a good answer for, right? Imagine, banking data for giving loans or not giving loans, right? How do you label that data? In particular, whom do you give loans, whom do you not give loans, right? Those are all privacy questions, all important questions. I don't think we have good answers to many of those questions at this point in time. And in fact, labeling the data is often up to the people looking at that data and assigning a label to it. And every company, every research group can do that in the way they wish to do. If it's not a publicly available data set, then they want to benchmark on this publicly available data set. So at this point in time, I don't think there's any safeguards as to how do you label your own data. And things go wrong there. In fact, I'm on camera, I have to be careful what I'm saying, but companies have used data sets and then put the resulting classifiers into, say, cameras, and then apply those cameras in markets for which they were not trained. And the algorithm coming up with results that were just not appropriate. Now, if you want to have more details for that, then maybe we can do that offline. But there is those examples.
What you didn't talk about is storing data. What are the consequences of storing all this junk?
Yeah, very good question. I mean, why do you think many of those companies have huge data centers? In fact, why do you think the US government, NSA, have those huge data centers with a lot of servers built in? I don't want to know how many petabytes of information they are storing in their data centers. Huge amounts of data. But there is technology out there. I wouldn't say it's very effective and efficient these days, but there's probably more data created than they can store, but they'll figure out a way to quickly weed through what they don't need and then just store whatever they deem to be important. Whether that is really what is important to them, that's another question.
Now, did they erase that stuff they don't need? Or they just, it's just heated and air conditioned and what else?
Well, I'm pretty sure if someone thinks that data can be put to use later on, they'll probably keep it.
Can we continue to store data like that? As much as we get 300 YouTubes a minute?
At this point in time, we can. Whether we eventually may not be able to do so anymore, it's a good question. I would not know. At this point in time, we just buy more hard disks. We have a lot of hard disks in our research group as well, just to store all this data. What do you mean by the original people?
The people that were developing the first AI. When you said back at the...
But yeah, I guess the question was, what did people think originally about AI when AI was developed? And I guess people were very excited back then, right? Some of the comments that I showed, Marvin Minsky, 1970, in 3 to 8 years, we have artificial intelligence on the level of humans. So they were very excited and encouraged about this. And I'm not sure they were asking all the critical questions that we are asking back then, largely because the problem of needing huge amounts of data did not arise back then.
Well, how do they measure how smart the AI was?
How did they measure how smart the AI was? Right, one of them was game AI, was a big part of this. Right, so using the game of checkers, and game of checkers was pretty popular back then, and having that play against reasonably trained humans. In fact, Arthur Samuel, from whom I showed the picture, I think had the first program that was able to compete with humans with reasonably trained humans on an accurate level. Now later on, it was the game of chess. Eventually, it was the game of Go. And the reason it went in this order was that checkers was easier than chess, which in turn was easier than Go. I guess there was one question over here. I need to be a little...
This will be the last question. And Alex will be around.
I'll be around. If you have questions, just come up.
Some polite people are just waiting, listening to him. Go ahead.
Can you repeat the question? Yeah. Yes.
Congressman didn't really know that much about big data and all that stuff, but what if someone like you does ask him?
What would I ask him if I had a chance? I guess one of the questions that is really important that I also mentioned at the very end of this talk is what data, what personal data is actually stored and no one knows at this point in time. And do we at least need to know do people need to have access to the personal data? And do people need to have a mechanism delete data which they don't want the company to be stored or to be used. And I think many of those mechanisms these days are not in place. And companies are just sifting through and trying to get as much data as possible. And I think those are the important questions that if there is no regulation, no one will, people will just grab whatever they can grab. So regulations have to be put in place eventually.
We have HIPAA, and that's in place, and it's completely out of sync with Facebook.
I have to say that I'm not aware of or familiar with HIPAA.
It's medical privacy, medical data privacy.
Okay.
Nobody's allowed, your wife is not allowed to see your data unless you sign a document saying so.
Okay. Apparently, we pay for it with our data, right? So in a sense, we are voluntarily putting up data. So you're actually, by uploading that data, I'm sure you're signing for Facebook to use that data. You agree to the terms and conditions. But are those the right terms and conditions? That's, I think, the question. Are they allowed to use those terms and conditions?
Okay, on that positive note, I guess.